All right, we will get started. Hope your weekend went well. We're going to continue on just a little bit because we didn't get a chance to talk quite enough about radical polymerization. I want to talk briefly about combustion, and then we'll move on to the last portion of the class. The reason I want to talk about radical polymerization is simply because it's, of all the places you encounter chemistry in your day-to-day life in the modern world, plastics and polymers is probably the most common one. I believe we started talking last time about polyvinyl chloride, which is made, and again, you don't necessarily need to worry about scribbling all of this down as fast as you can. I drew it in advance to facilitate the discussion, and you'll have access to these notes online. This molecule is vinyl chloride. Remember that the sp2 hybridized carbon involved in a double bond is called a vinyl carbon or a vinyl position. And the polymer is formed starting with a radical initiator that the single electron attacks the pi bond to create a new sigma bond with the other electron from the pi bond left behind on the carbon that's more substituted because the radical will be more stable there. In particular, though I haven't shown that here, lone pair electrons on the chlorine can stabilize that radical by resonance. And there's a resonance structure you could draw in which there would be a pi bond here and an unpaired electron on the chlorine. Then that resulting radical can attack the pi bond of another vinyl chloride. Again, these half-headed fishhook arrows used to describe motion of one electron. We make a new bond in red and we make a new radical, and so on. We continue to tack on additional vinyl chloride subunits. In polymer chemistry, we call these individual subunits monomers, and when they're stitched together, it's a polymer. And so here is a section of a polyvinyl chloride polymer. You can see the individual subunits in black with sigma bonds made during the polymerization process in red. And so you have this alternating pattern of bonds with chlorine and then carbons that aren't bonded to chlorine. Go ahead. Are all polymers made through radical polymerization? No, there's lots of different ways to stitch subunits together. So one of the most common polymers that contained my Diet Coke this morning was PETE, polyethyl terephthalate or something like that. I think that's a polyester instead of a radically polymerized process. So there's a lot of different ways to make polymers. The ones I'll show you today are available through radical polymerization. PVC is used for pipe fittings, hoses, flooring, lots of different things. Anytime you hear the word vinyl, it probably is related to PVC. It has the recycle code 3, so you can check all your plastics and see if it's PVC. PVC tends to be quite rigid, for reasons we talked about last time. Polymers, their properties are determined by their functions. And in the PVC polymer, the individual monomer units and chains can pack against each other in a tight sort of crystalline structure. And the tighter they pack, the more rigid the polymer is. And so in order to make PVC polymers less rigid, you can include a type of molecule called a plasticizer. And the plasticizer gets in and binds to the individual monomer subunits of the polymer and makes it more favorable for the polymer to have a looser, more extended conformation where the polymer will be quite a bit less rigid. And I think I alluded last time to my industrial strength hose that I bought in San Diego and was really quite bendy and useful. It didn't kink a lot. But then when we got here The hose is, I guess, more than 10 years old at this point, so maybe hoses don't last that long. But after sitting out in the sun and in the heat, these plasticizers, small molecules that were inside the polymer matrix, sort of preventing it from becoming rigid, had leached out and the hose began to crack. And this is why when I turned it on, there were lots of sprays in various places that they shouldn't be, it became inconvenient. I replaced that hose this weekend with another hose that in another 10 years will be cracky and spraying out. Anyway, another issue with polymerization is the potential for branching. What I've shown you here so far is just one monomer added on at the end of the chain and so on. And you can control how long the chain is by the ratio of how much radical initiator you add versus how much monomer is present. You might imagine that if you add a lot of radical initiator relative to monomer, you're going to be forming a lot of chains and you're going to run out of monomer faster, so your chains are going to be shorter. Whereas if you add a smaller amount of radical initiator but a large amount of monomer, you won't have that many chains started, so they will continue to get longer and longer until you run out of monomer. Branching can occur in these types of polymers because the hydrogens that are in the main chain of the polymer can also be removed by radicals. And so depending on the circumstances, a growing polymer chain might abstract a hydrogen from another chain. That would terminate the one chain, causing that to be over, but it would create a radical in the middle of another chain, and again, it would selectively be on the more substituted carbon where it's more stable. And at that point, we can start generating a new polymer site from that location. So again, attacking the pi bond of the vinyl chloride monomer to create a new radical and make a new bond, and we can continue to branch from there. And so there are various industrial ways to control the extent of branching, but one of the main consequences of branching is it controls how tightly the polymers can pack against each other. And that determines how flexible or rigid the polymer is. And the classic example of that is polyethylene polymers. So polyethylene is just radical polymerized ethylene. There's no R group, there's nothing other than hydrogens on those carbons. And so your polymer is literally this just long hydrocarbon chain. If the process, and the individual subunits are highlighted in pink here, if the process allows for a lot of branching, then you can get polymer networks where the individual chains don't pack against each other very well. It would be difficult, for example, to generate tight van der Waals interactions between chains, which you can do in just linear chains where they can sort of pack against each other in zigzag fashion. That kind of packing generates strong van der Waals interactions. That's induced dipole interactions. And that's the kind of thing that the high-density polyethylene can do. So Hdpe, or high-density polyethylene, tends to be more rigid and a stronger container because there's no branching. So polymer chains can pack against each other quite tightly. The branching gets in the way of that and prevents that. So you'll see low-density polyethylene in tubing, food containers, those little plastic containers that they put your salad in at Zupa's or whatever, are probably low-density polyethylene. High-density polyethylene, I think one place I've seen that is in washing detergent bottles, that big, thick plastic. Polystyrene just has the thing that comes off of the vinyl carbon as a benzene ring, and there are branched and linear varieties of polystyrene. It's used all over. It can be brittle, but it also has the property of it can be foamed into packing peanuts, which is but they're squeaky, which is annoying. Sporks are made of polystyrene, although I don't know that sporks are a thing anymore. There's mostly forks. I don't know. Used to be when you went to Taco Bell, they would give you a spork, but nobody here knows what a spork is. It's the fork that's also a spoon. There was a VeggieTales Lord of the Beans where the sporks were the bad guys. Sporks for orcs. Polypropylene has got a methyl group coming off the vinyl carbon. Polypropylene tends to be more resistant to mechanical stress. It's also more chemically resistant. In the lab, we use a lot of organic solvents to do our stuff, and some polymers will distort their shape and sort of melt in the presence of organic solvent. For example, with polystyrene, you can dissolve some polystyrene with acetone, but polypropylene is resistant to a lot of different chemicals. Vinyl acetate is one that you may have eaten at some point in your past. Elmer's glue is vinyl acetate. It polymerizes in air. It's got an oxygen coming off the vinyl carbon, and then it's tied up in this ester. Paint often has a base of vinyl acetate that polymerizes the paint and allows it to stick in a smooth surface. Wood glue, envelope adhesive, so you can lick this stuff and it's fine and it doesn't hurt you. Teflon is one that you have definitely encountered before. It's tetrafluoroethylene, and then polymerized. Instead of carbon-hydrogen bonds, you have carbon-fluorine bonds. And carbon-fluorine bonds are interesting. They don't really like to hydrogen bond with water, and they also don't really like to be near hydrocarbons. So Teflon's an interesting polymer because water beads up on a Teflon surface, but so does oil and grease. At least it does until you scrape it off your pan into your food, and then your pan starts to stick stuff again. Folks that might be interested in a career in dentistry will encounter dental composite, which is also a radically polymerized process. If you've ever had a filling at the dentist, you're sitting there with your mouth open and he's asking you how your day's going, and you're saying, oh, and then he says, stop talking, I'm trying to do something, and puts the filling in after he drills the whole, doesn't that just make you, drilling the hole in your teeth, and then packs the tooth with dental composite, and then he takes this ray gun looking thing, and you see a blue light in your mouth, and he shines it on there for a couple of seconds and then pulls it out. What they're doing, what the dentist is doing there is, this is the dental composite molecule. It looks really horrible, but actually it's just basically polypropylene with two individual propylene molecules linked together with this larger linker. It's called BPA, which refers to this segment, glycidyl methacrylate. But when you do the radical polymerization, you make a polypropylene chain where instead of just being methyl groups here, you also have the branching linkers between chains, and that generates a highly cross-linked, and it's not as orderly as that. One chain might be cross-linked here, and then here they're linked to another chain, so a dense network of polymer that holds the filling in together. Questions about any of these polymers? Just sort of a survey. Yes?
Okay, am I remembering correctly, isn't there some people out there that are like some products claim BPA free or stuff like that? Is there any downside to BPA?
Yeah, let's talk about that. Caroline's asked about BPA and is there a downside to it, because you've probably heard of things that are BPA free. So bisphenol A is what BPA is. It's got two benzene rings linked together by a quaternary carbon with 2 methyl groups on it, and then either benzene ring has an OH group. And it happens to be a convenient scaffold for polymers. It's not just in dental composite, but in some other polymers, especially epoxy type polymers. There will be things branching off on this side and on that side, and it's just it's a useful way of cross-linking individual polymer chains. However, if you've shopped for baby bottles or shopped for soup or other things that are held in cans, you might have encountered the label BPA free, or on the can of tomato sauce it might say the can liner, which is usually some kind of epoxy polymer. It does not contain BPA. What's the big deal with bisphenol A? Well, it can bind estrogen receptors, though with dramatically lower affinity than estradiol does. So here is the structure of estradiol. Like bisphenol A, it has a phenol functional group. And then on the other side of the molecule, there's not a benzene ring, but it sort of has those 2 OH groups at sort of similar distances. And so there's some concern that if BPA leaches out of a polymer, it could have unintended developmental effects. And so the FDA bans its use in baby bottles. The risk is still controversial, and this leads to the concept of the precautionary principle. And this is the argument that if there's even a chance that a chemical could be dangerous, we should treat it as maximally dangerous until the evidence suggests otherwise, with the goal of protecting ourselves. The challenge is that there's risk inherent to everything, and so you want to make sure you've got a clear risk versus rewards analysis before you make a decision. That being said, often the market will demand what consumers want, and consumers apparently don't want BPA leaching out of their plastics, and so more and more consumer people, more and more industrial folks are leaving BPA out and choosing other methods. Let's see, what else?
I had a quick question.
Yeah.
I was just wondering how these chains get terminated with the radicals still on them.
Okay.
Is there like a proton that gets donated, or is it something else?
Yeah, so let's talk about chain termination. Basically, in order for a chain to terminate, this is an example of one chain termination process where the radical end of an elongating chain abstracts a hydrogen from somewhere. There are other chain termination events that you could imagine. You could imagine one radical chain finding another. But in a lot of cases, it doesn't matter, because in terms of mass and polymer identity, only a very, very small amount of what you put in is going to be on either end of the polymer. And this is odd. It took me a while to understand this, but by far the properties of the polymer are determined by the monomer and not what's on either end, because as a percentage, what's on either end is only a very small part of the polymer. All right. Anything else you want to talk about polymers? Let's see. Last time, I think antioxidants came up, so I thought I'd just say a little bit about that, because sometimes folks are interested. You may have heard of antioxidants before. A classic example of antioxidants is this molecule resveratrol that's present in grapes and a lot of other foods. The reason this is an antioxidant is that a radical can easily abstract a hydrogen from the phenol oxygen, and the resulting radical is pretty stable because it can be delocalized by resonance into the benzene ring and all across this highly conjugated molecule. So the goal, oh, we turned Siri on, that's weird. The goal for antioxidants is to have a molecule that's very stable as a radical so it doesn't go on and react. It's kind of like a radical trap. Here's another one that I think comes from green tea. It's epicatechin 3 gallate, and it has a lot of these OH groups on benzene rings. In fact, they call these antioxidants polyphenols because they've got a lot of these phenolic OH groups that can quench other radicals, right? The idea is that once you've removed a hydrogen from the polyphenol, the molecule you had is no longer reactive, and the polyphenol isn't either. There's some controversy over whether it pays to take antioxidants or not. The NIH website on the subject says that clinical trials really haven't shown any dramatic effect for various reasons in terms of taking antioxidant supplements. There are different arguments as to why the clinical trials might not have shown a strong effect. It probably isn't worth a huge amount of money to pay for antioxidant supplements. Anybody that's trying to sell you something by telling you it has antioxidants in it it's probably mostly marketing. That's my favorite line from the movie Home with, I don't know if you guys have seen that. It's where you have this purple alien whose name is O, and his friend asks him whether the enemy alien Gorg super chip is really super, and he says, it is mostly marketing. And that may be the case with antioxidants as well. Okay, there's a question. Now, you should eat a balanced diet and all of that stuff, but none of these molecules are likely to be an end-all to all of your problems. Let's see, is there a limit to how many radicals could be on an oxidant? I think as you continue to remove abstract hydrogens, that ends up being an oxidation reaction, and there is probably a limit. I don't know what it is. Let's see, there's another question. What determines if a polymer can withstand the microwave or the dishwasher? And Wallace answered, and I think he's right, in many cases it's the issue of melting point. So like any other molecule, polymers have melting points. That is, how hot do you have to get it before you overcome the intermolecular forces that are causing the polymer chains to like being next to each other versus not. And the identity of the side chain group, the presence or absence of branching can influence that. So for example, you would predict high density polyethylene to have a higher melting point than the low density stuff. And so some of these you might be able to put on the lower rack of the dishwasher and they won't get all melty afterwards. Others you might not be able to do that, and it will just depend on what the melting temperature of the polymer is. And you can probably Google, I haven't done that, but you can probably find on the internet what kinds of polymers are more stable to those conditions. One of the worst incidents that I had with polymers was when I started the oven, but there was a Tupperware container of cupcakes in it, and that stuff started to melt and drip all over the place and then start to smoke. The great thing about the plastic, though, is that you just turn off the oven and then you let it harden, and then you can just pull it out of there without wiping it all over the place. Oh, and I forgot, polystyrene. You can have lots of fun with polystyrene. Anybody ever heard of shrinky dinks? No? Shrinky dinks are this thing from the 80s that sort of made a bit of a comeback, at least at our family. It's a polystyrene sheet that has been pulled outward into and spaced out to be more flexible, but it's not a very stable situation. And when you heat it up, the polymer snaps back to a much smaller shape. So you can create lots of little things for your friends, keychains and whatnot, by drawing a picture on the polystyrene sheet and putting it in the oven, and then you can watch it shrink. I go back and show you a video, but I don't dare open my Photos app for fear that you'll see another of my before images. Maybe I'll look for the video we did last year during the first days of the pandemic, when we were desperate to find something entertaining to do at home. We had the kids do Shrinky Dinks, and there were Baby Yoda Shrinky Dinks. I did a Mandalorian helmet and the symbol of Death Watch, but it's kind of hard to figure out what to do with these things once you have them. So anyway, it was entertaining for a while. Yeah, you can do them with plastic takeout containers. Make your own Shrinky Dinks. That's pretty fun. Let's see. Lastly, I just wanted to mention combustion, which is a radical process, and one of the ones that humans have been doing for like ever. And combustion is highly complicated. We're not going to do wood combustion. We'll just do methane combustion. Basically, oxygen, molecular oxygen, is a diradical. It exists if you go, I mean, you've drawn oxygen perhaps before in general chemistry with that Lewis structure, and that's fine. But if you look at the highest energy molecular orbitals in oxygen, they're the same energy, and they're basically singly occupied. And when the two electrons have the same spin, that's called triplet oxygen. And triplet oxygen is a fairly stable form. But if you excite oxygen, you can get singlet oxygen where the spins are anti-parallel. And singlet oxygen is highly reactive. And instead of drawing it like you may have drawn the Lewis structure of oxygen, it's more like a reactive diradical. So you need a source of heat or a spark for ignition for combustion, because you've got to generate some singlet oxygen. Once you do that, one of the radicals on oxygen can abstract a hydrogen from methane to generate this methyl radical. And there are a lot of different things that can happen at this point. I thought maybe I'd show you at least some of them that would, let's see if I can find my paper, some of them that would result in CO2. Here we go. None of this would be stuff that you needed to memorize or anything, but also present when you're doing combustion is a hydroxyl radical. So you could imagine forming methanol through a radical process. Then once you had formed methanol, the hydrogen on the oxygen might be removed by some other radical, perhaps a hydroxy radical. That would make water out of the hydroxy radical and would make the following methoxy radical. And once you've got that, some interesting fragmentation can happen where you generate a pi bond and you release a hydrogen atom. All of this sounds like chemistry that's sort of crazy, but it can occur because it's a very high temperature. And you can continue on, and I won't show you much more of this, but you can continue on until you've oxidized the oxygen to CO2. So combustion is not as simple as you may have written the balanced equation in general chemistry, where you have a certain number of carbons and hydrogens and you add a certain number of oxygens and you make CO2 and water, and then you have to balance the equation, and maybe if we do this or something, you get there. It's actually a lot more complicated than that. And engineers, particularly chemical engineers, have worked really hard to model this process, and it's just sort of beyond the scope of what I know. But when you blow out your birthday candles, you are quenching a radical process and spreading disease, so knock it off. Okay. So that's sort of it for the reactions. The rest of the class is going to be, how do we know what we know? How do we know what we know in chemistry? How do we confirm when we've done a reaction? How do we confirm that we've got the molecule that we think we're making? Chapter 13 describes two techniques. One is called mass spectrometry, and the other is called infrared spectroscopy. Okay, and these are fairly easy to understand on your own, so we're not going to talk about them a lot in class. Mass spectrometry gives you the molecular weight of a molecule. It's a highly technical technique. You basically have to put a charge on a molecule. You can do that either by removing an electron from it or adding an electron to it, or you can add a proton, maybe make the conjugate acid of a molecule. But once you have charged the molecule, you put it in a magnetic field, and its trajectory through that magnetic field tells you something about what the mass of that molecule is. There's a lot more to know, but not a huge amount that you will use. In mass spectrometry, you have on this axis, the data you get on this axis is just sort of intensity, which means number of observations. You have a little detector that counts how many times you see a particular molecule. And on the x-axis, you have mass divided by charge, which is sometimes called the m/z ratio. And this is because the physics that determine how this works rely both on the mass of the particle and on the charge of the particle. But basically, you will see a peak in the mass spectrum, and you will look at that number, and suppose it's, 1431 or something like that. You would look at the molecular formula for your molecule, and you would confirm that the mass you see here is consistent with that molecule. So some people in the past have tried to use mass spectrometry to determine a lot about the connectivity of a molecule, and you can, but there are much easier ways to do it now. So honestly, what most of us, at least in the organic area, use mass spec for is to confirm that our product has the right molecular formula. So there are a couple of things that you should still do the Chapter 13 study guide. There are a couple of things about mass spec to pay attention to. One is the characteristic pattern in molecules that have chlorine or bromine. For chlorine, you have two different isotopes available to you, chlorine 35 and chlorine 37. For bromine, I forget what the isotopes are, but they're also two mass units apart. I should just look it up. I should know this. Anyway, I believe for bromine it's 79 and 81. If a molecule has chlorine in it versus bromine, that for and the height of those two peaks will depend on the relative abundance. So one of them is 1:1 and the other is like 3:1. And I don't remember which, but that's one thing to pay attention to in the study guide. Infrared spectroscopy is about detecting bond stretches and vibrations. So in methane, for example, you can think of each of these individual carbon-hydrogen bonds as a spring, and each of them can vibrate, and there are various vibrational modes. For example, you might imagine both of these bonds stretching this way at the same time as both of these bonds stretch that way. That process is quantized and responds to particular wavelengths of light that are in the infrared region. And different functional groups vibrate at different frequencies. And so in an infrared spectrum, you will see characteristic peaks that represent different functional groups. So once you have a molecular formula, infrared spectroscopy is a good way of determining what kinds of functional groups might be present in a molecule that has that molecular formula. So your text will list a bunch of different functional groups and the areas of the IR spectrum that they appear in. The infrared spectrum is typically displayed in a pattern like this. On the y-axis you have, let's see, I think it's percent transmittance. This is like absorption, only it's like 1 minus absorption. So up here would be 0, or up here at the top would be 100% transmittance. That means all the light gets through, nothing is absorbed. Here would be 0%, meaning none of the light gets through, everything's absorbed. And then here is wavelength, only it's expressed in a weird form. So wavelength typically describes the distance from one wave crest to another, and it's typically in meters of some kind, nanometers, centimeters, whatever. If you take 1 over the wavelength, that's related to frequency, but it's not quite. Do you remember from physics that the speed of light equals the wavelength of light times the frequency of light? And do you remember from physics that the energy of a photon of light is equal to Planck's constant times the frequency, which would be the same as saying the energy of light is related to the speed of light times Planck's constant divided by wavelength? So if you take the wavelength and if you divide 1 by the wavelength, the reciprocal of the wavelength is directly proportional to energy. Why don't they just convert this into frequency instead of wavelength? I don't know. It's a traditional thing. But the term 1 over the frequency is called wave number. Instead of how many meters per wave, it's how many waves per meter. And typically the units are, again, for weird, inconvenient purposes, 1 over centimeter. Okay? I don't get it, but it's usually from low numbers on the right to high numbers on the left. High energy vibrations, low energy vibrations, and we call that axis wave number, and the units are inverse centimeters. But what that means is that peaks you see over here are higher energy vibrations than peaks you see over here. The typical IR spectrum will stretch from about, 800 wave number to about 3,500 or maybe 4,000 inverse centimeters on that edge. And typically the area between, 800 and maybe 1,200 is called the fingerprint region. It's unique to each compound and it's difficult to interpret. Some people do, but we won't worry about it. This area in this region, though, has characteristic functional group peaks. For example, a molecule that has a carbon-oxygen double bond will generally have a sharp and intense peak in the 1600 to 1800 wave number region. A molecule that has an alcohol will have a broad, intense peak at in the sort of 3000 to 3500 wave number area. There's a lot you can do with infrared spectroscopy, but for our purposes, you're basically going to be looking for carbonyls and for OH groups. Yes?
So it's saying that it'll do that change if it has a OH group. What happens if it has multiple?
If it has multiple groups, depending on the energies of those different groups' vibrations, they might coincide in the same peak, or you might see two different peaks. These infrared peaks are fairly broad, though, so probably you would just see one. Okay. What else? So you can look in your text and see the characteristic functional groups that see the functional groups with their characteristic peaks in the IR. Again, you're going to use that in addition to other information to get a sense for what the molecule might be. Be sure you know how to recognize the carbonyl peak and the OH peak. We don't have enough time to delve into it in any more detail, but I think you should have the tools to be able to use it and gain useful information from these two pieces of data. Now, let's talk about connectivity. That is, who's bonded to whom? If your product is indeed this 3-carbon alcohol, how do you know it is that particular isomer versus the other available isomer? If we look at the differences between these two, in the molecule on the left, we've got 2 CH2 groups and then 1 CH3 group. In the molecule on the right, we instead have 2 CH3 groups and 1 CH group. So, and then both of them have an OH group. There's clear differences in connectivity. How do we detect that? And the answer is a technique called nuclear magnetic resonance. Okay, or NMR. So this is a technique that's based on some nuclear physics, but the great thing about this technique is you don't have to understand why it works to be able to use it. So what I'm going to tell you is an oversimplification of how the process actually works, but it will be useful enough to get you what you need to know. All right? So the idea here is that some nuclei have non-zero spin. Protons and neutrons each have a characteristic spin, just like electrons do. And depending on the number of protons and neutrons a nucleus has, that nucleus might have a non-zero spin or non-zero angular momentum. The proton, just a single hydrogen, or the isotope hydrogen 1, just is a nucleus with just one proton in it, is a spin 1/2 nucleus. Its spin can be either plus or minus 1/2. Okay? And for charged particles, when they have a non-zero spin, that means they have a magnetic field. Okay? So you can think of a hydrogen atom as being a tiny magnet. Which means it could be responsive to a magnetic field. So we will sometimes represent the spin of a hydrogen atom with just this arrow. So you've got hydrogen, and we'll call him hydrogen atom A, and he has that particular spin. Plus 1/2 or minus 1/2, up or down, same thing for our purposes, okay? So principle 1 is protons are little magnets, and because of that, they can be responsive to magnetic fields. So if you put the proton in the presence of an applied, strong, we'll call it an external magnetic field, that is a magnetic field that we turn on that has nothing to do with the proton itself, and sometimes we represent it with an arrow like this. Again, this is just sort of junk physics because I don't understand all the details. And this will refer to B, with the little 0, will refer to the applied external magnetic field. When you add that magnetic field, you suddenly create a difference in energy for that hydrogen atom depending on the way it's oriented, okay? So if a proton can have up spin versus down spin, without a magnetic field, up spin versus down spin states are equal in energy. It doesn't matter, right? They're degenerate. The difference in energy between the two is equal to 0. So the population should be something like 50% up and 50% down. When you apply the external magnetic field, though, you now create an energy difference between being aligned against the external magnetic field and with the external magnetic field. So with the field is lower in energy versus against the field is higher in energy. If there's a difference in energy here, that means that there should be a difference in population, right? It's just an equilibrium constant. If it's lower in energy to be aligned with the external field than be aligned against the field, you would expect that more of the protons should be with the field than against the field. Now this change, this difference in energy is very small. And in fact, you know, in terms of percentage-wise, it's still only like 50.001% with and 49.999% against. But even though we're working in the thousandths place, that difference in population is enough for us to sense. The energy difference, as I said, is very small. If you figure out what frequencies are in the right range to make a proton jump from the aligned spin state to the opposed spin state, the photons that can do that are in the radio frequency. So you're looking at wavelengths of centimeters to meters instead of visible light frequencies. So basically, we're going to be radio frequency waves to cause a proton to jump from an aligned spin state to aligned against spin state. This difference in energy is going to change depending on the kind of proton we have, and we're going to use that to determine what kinds of protons we have in the molecule. So we'll continue with that next time. You should be working on study guides 13 and 14 for the future. Chapter 15 we finished today.